Classes in Statistical Mechanics. Lectures by Professor George Phillies, based on his book Elementary Lectures in Statistical Mechanics, Springer Verlag, 2000. And today, this lecture is Lecture 21. In any event, we are going to return to where we were, and we have been discussing symmetry and correlation functions. In our lecture last time, we discussed the density operator, which is simply a complicated way of saying the density at a point in space. The issue is that we have capital N particles in the system, and the density is the sum of the likelihoods that each of them is at a point. And we can use direct delta functions to convert from where are all the particles to what is the total likelihood of finding some particle at a point. We're now going to continue to discuss correlation functions and translational variance. It's an example of symmetry. And we will discuss the spatial Fourier component of the density. This is page 295, equation 22.12. And the first line on 22.12 is just the orthodox definition of the spatial Fourier component of the density of particles, namely it's the sum over of e to the ik dot r, r being a particle position, over all particles. You can rewrite that using the density operator delta of r minus rj, and the next two pieces of the equality, which are really just identities, get you to a definition in terms of the density of particles in the system as opposed to their locations at one time. You could also do the same transformation with respect to the momentum and obtain the spatial Fourier components of the momentum in the system. The one difference between 2213 and 2212 is that in 2212 we just assign each particle value 1. So if we add up all of the particles, we get n. In 2213 we're saying that each particle j has associated with it a momentum p sub j, and we are computing the spatial Fourier transform of the density of pj, the p's at different points. So there's this extra variable there. So what is the average value of a sub k? Well, it's given by 22.14. In 22.14, the one thing we have done, this is bottom of page 295, is to say a sub k is the sum of the e to the ik dot rj's, and we will say, since all of these are the same, we will just copy one term and multiply it by capital N. The next thing that we've done is to say that, as has been true in fluid systems so far, the potential energy is determined by the relative positions of pairs of particles. We have a particle here, we have a particle here, they're some distance apart. If we translate the two of them, the potential does not change. And therefore we can write the potential energy in terms of the vectors, which are the positions of all of the particles with respect to some one particle, which we've chosen to be particle 1. And so in 22.14, we have split out the position of particle 1, and the potential energy is going to be the same no matter where particle 1 is, assuming all the other particles keep their relative positions. Okay, so what is the value of a sub k? Well, suppose I look at particle 1 at some location, and I translate it, and I translate all of the other particles at the same time. The potential energy of the state where particle 1 is here, and particle 1 is there, and all the other particles are displaced the same way, is the same. Therefore, the statistical weights of being here and being here are the same. And when we add up over all possible values of r1, we have an integral of e to the ik dot r over a large volume. Well, what does that integral do? And the fast hand-waving smoke and mirrors answer is it averages to 0. But if you think about this carefully, this bothered me when I was in what we would call E&M 2, or really 1120, except of course we got as far as plane waves, is that, well, we have a wave that oscillates, and if it has an integer number of oscillations within each integer oscillation, the integral goes to 0. But then there's this little piece at the end which may not be exactly an integer. And therefore the statement that integral e to the ik dot r times over the volume of a big system is 0 is true up to a surface effect that is one wavelength thick. So it's a good approximation, but it's not perfect. But that's good enough. Now, if you are doing light scattering or neutron scattering or X-ray scattering, for that matter, microwave scattering off a big fluid, there's one additional little feature which is different from quantum mechanics or solid-state physics. The vector you have due to scattering in any of these methods can be any value you want. You just change the scattering angle. If you talk about, for example, electron waves in a solid, the waves are required to go to 0 at the edges. Ditto sound waves in a solid. However, the scattering experiment is traditionally done on an open volume, and therefore the wave doesn't have to be 0 at the edges of the collecting volume. And thus there's some little differences there. Now we'll do the symmetry argument. The symmetry argument invokes translational invariance. And I am giving the very careful form of the symmetry argument, not the hand-waving form. Okay, the potential energy depends only on the separation between the particles, not the absolute position where all the particles are in space. Now, if you think about a crystal clamped in a vise, there's an issue here, and I'll point out what it is in a bit. But let's just say the potential energy has this property, and we're somehow ignoring surface and wall issues. Okay. In that case, any change in the positions of all of the particles that does not change any of the Rij, any of the particle separations, does not change the statistical weight. For example, if we translate all of the particles through the same displacement, A, the vector, the statistical weight of the system is not changed. So far, so good. Okay. Now let us consider the same calculation done in two sets of coordinates. And the two sets of coordinates differ from each other in that r prime is equal to vector r plus a vector a. That is, for the r prime system, we have displaced the origin distance minus a vector a. Okay? Now we're going to average e to the I k dot r and e to the I k dot r prime. Well defined, we're going to calculate the same thing in two coordinates. Okay, if we go through the average, for every state in which r, actually it's the full set of all of the r sub I, has some set of values, there's an exactly corresponding state in which r prime has exactly the same set of values. These are not the same set of the system. If I am, we'll take particle 1's x coordinate. If x is equal to 10, it's here. If x prime is equal to 10, well, x prime is x plus a. If x prime is equal to 10, the particle is now over here. Yes? So the two particle locations physically are different, but they have the same numerical values of the coordinates. Yes? Mm-hmm. Okay. Well, since the two states have the same numerical values of the coordinates, except it's r in one case and r prime in the other, the e to the I k dot r, the spatial Fourier components of the density for those two specific states, must be equal to each other. Also, by translational invariance, because the potential energy does not change when we compare this state and that state, the statistical weights must be exactly identical. Okay? So the statistical weights are the same. The a sub k is the same function of r that it is as a function of r prime. The functions being averaged and the statistical weights are equal point by point, and therefore the allowed list of points are the same, and therefore equation 22.15 follows. So a sub k is the same whether you calculate it in the r coordinates rather than the r prime coordinates. Yes? I have not shown you that either of those things is 0. I've shown you that they're equal. Now, one way we could advance and do this calculation is to say we're going to take the right-hand side of 2215 and do a change of the variables and replace r prime with r. Well, actually, you replace r prime with r plus a, and that's seen in 22.16, where, bottom line, r prime has been replaced with r sub j plus a. Yes? The potential energy does not care about the change in coordinates because we only care about separations between particles, and the potential energy is the same number before and after we've made the change of variables. So each of those things is an orthodox ensemble average, and we can compress them because we remember what the spatial Fourier component of the density is, and you can compress them into 22.17, which says that a sub k average is e to the I k dot a sub k average, and that's true for an arbitrary a. Yes? And you might say, well, gee, that's implausible unless a sub k average is equal to 0. Yes? If you have this number, and you multiply it by a complex number, e to the I k dot a, and you get back to your starting point. And what number can you multiply by anything and get back to the starting point? 0. And now we will give the warning. Finding counterexamples is a learned art. It's challenging. It's the reason mathematicians are not the same as physicists, because essentially all mathematics is proven by demonstrating that any counterexample is self-contradictory. This is why mathematicians are very sensitive to something called the Axiom of Choice, which is central to that. Let us now prove this by demonstrating that my claim is wrong. I did not just prove a sub k average is equal to 0, and I will now give the counterexample. Suppose k vector is equal to 0. Yes, that's certainly a legitimate value of k. But if k vector is equal to 0, e to the I k dot a is 1. And quantity equals quantity should not be surprising no matter the value of quantity. On the other hand, if k vector is 0, it's very easy to calculate the average value of a sub k, and you discover it's n over v or something like that. That's a homework problem. We'll assign it. And therefore, you have to be careful. You can be tricked. Okay. Now, having said that, we didn't say anything about the state of matter in the system. we just said that we can ignore wall potentials. Now, if I tell you for a liquid that A sub k average is 0, that's not surprising, because the fluctuation with this wave vector is equally likely to have every phase, and therefore averages to 0. Let alone it can have all different amplitudes, but it's equally likely to have every phase for all those amplitudes. What about crystals? If you hunt back in the literature about 30 years, you can find a more or less completely wrong Physrev letter, which made several interesting claims about statistical mechanics not working for crystals, based on the observation that e to the I k dot a average in statistical mechanics is 0. They basically use this proof to show that. The reason the paper is wrong was that they asserted that the spatial Fourier components of the density in a crystal, given the other statements I've made, are non-zero, and that's wrong. In order to understand why it's wrong, we have to remember, here's our pretty crystal, and you can see the spatial Fourier components of the density because they're printed on the side of the box. However, we said the wall potential is negligible, and therefore the likelihood of finding our crystal here, or here, or here, or here are all the same. This is the crystallography experiment, in which you have mounted your crystal not in a vise with steel jaws, but in a vise with jaws made of marshmallow fluff. And since the jaws are made of marshmallow fluff, the crystal is equally likely to be any place, and its average density is uniform inside. But you have to be careful to make those arguments correctly. Well, having said that, you could also do the opposite and say, let's make a really good vise. And there was a group at NIST, this goes back 40 years, that made a vise where they could not only hold the crystal still, but they could translate it with a position sensitivity of about 1/100 of an angstrom. And they then scanned this crystal in front of an X-ray beam and were able to count the lattice planes as they went by while knowing the spatial translation. And they were thus able to determine Avogadro's number to some very high precision. Very clever experiment. There are also other symmetries, for example, rotational invariance and inversion invariance. The issue in rotation invariance is that in many systems the likelihood that, say, the momentum points this way or that way are exactly the same, and therefore, since the states are exactly equally likely, their average must be 0. This is plus p, some probability. This is minus p, exactly the same probability, and they sum to 0. Inversion invariance refers to the issue, let's suppose we take the coordinates onto their mirror image. Now, with molecules as opposed to spherical atoms, that's much trickier than it sounds. Did you just invert the coordinates of all of the molecules? Or if they're optically active, did you change them into their mirror opposites? If you just flip the positions of all of the molecules and don't flip their shapes, you now have a right-handed molecule that is stuck in a hole shaped like a left-handed glove, and the energy isn't the same before and afterwards. You also have, in addition to vectors that flip sign when you do the symmetry, the inversion symmetry, you have pseudo vectors. A pseudo vector has the property that when you take the coordinate mirror image, the sign does not change. Have we seen a pseudo vector? Yep, angular momentum, r cross p, If you flip R and the sign of R and the sign of P, L does not change. And I then go on to discuss, you get to read it yourself, propellarenes, which are molecules in which the direction of motion and the direction of angular momentum spin are correlated because they behave like little pinwheels. Okay, I will then assign, why don't we assign problem 2? And that ought to be good enough. And we now advance to a chapter I am mostly going to skip over on the stability of the canonical ensemble. It's very heavy mathematically. It's an issue that many stat mech books forget is there. But I will explain what the issues are, and this gets us eventually to the issue that thermodynamic quantities are constants of motion. Okay, so we are going to do an ensemble average. So we generate a list of all of the states of the system, and we calculate the value of the variable in each of those states, and we calculate the statistical weight of that state, and we do the averaging. Well defined? Anyone can do that. Now we come to an issue, what happens as time goes on? And I'm going to point back at chapter 2 very briefly, or 3. We can represent the state of the system by a point in phase space. That is, we have a list of all of the positions and all of the momenta. That's a 6n dimensional vector, and we can represent it as a single point in 6n dimensional space, phase space. As time goes on, if we watch the same system, the system moves through phase space. It moves through phase space because the particles are moving, so the positions are all changing. The particles are interacting with each other, so their momenta are changing. And therefore, the phase space coordinates of the particle keep changing. And so, if we think of phase space, it's filled with phase space points corresponding to states of the system. But as time goes on, the points move. And we now ask, since we've noticed this is time dependent, how we are going to observe it. And one answer is we will take the large filing cabinet full of all of the photographs of all of the states of the system, and we will link the photographs together as motion picture films, so you actually have the states linked together and you know which state follows the next. Of course, you will actually have an extremely large number of these motion picture films, not just one, because you can readily show that if you start at a phase space point, you don't actually eventually go through all of the other phase space points. You only go through a sample of them. Okay? And now we try imagining 2 experiments to test what happens as time goes on. And so what we do is, since we are at a large technical university, we take our continuously infinite supply of graduate students and we associate one with each phase space point. And now one instruction can be that we tell each student that she, he, or it, or whatever, is to follow, we may have graduate students from other dimensions for all I know, is to follow the phase space point as it walks around. And at some later point, the phase space point has moved, the coordinates have changed, and we will do the ensemble average a second time, and each graduate student will calculate the value of the function at the new location in phase space, and the statistical weight at the new location in phase space, and we will take a second average. Okay? The alternative to this is to say we will assign each graduate student a location in phase space. Yes? And they will sit there, and when I call out the second time, they will look, and will presumptively be some system in their vicinity, and they will do the calculation like before, and they will get the ensemble average. Yes? You do notice there are now two completely different ways to handle time evolution. The question is, are these the same or not? And it is very easy to do a completely wrong hand-waving argument that says they're the same. Where do you go wrong? The point where you go wrong is that the number of grad students I had to use is continuously infinite because the supply of phase space points is continuously infinite. Because the supply of students and points is continuously infinite, I am not allowed to use a counting argument. I cannot say I started with 3 states in this volume, and therefore there must still be 3 states in the volume. Counting arguments are invalid with continuously infinite variables, and I used to have, but have misplaced, an example that proves this. Okay. So where could I possibly go wrong? What could go wrong with this argument? Well, let's consider the second time average. We're each sitting at our phase space locations to monitor what's going on for quality control purposes. And we now, when I call out time, you now look in your little volume of phase space, and maybe you have one system there, and maybe you have 2 systems there, and maybe you have no systems there at all. And gee, unless you have one system before and afterwards, that's a counting argument, you have to do better than that to prove anything, your phase space argument will fail. Okay, now let's consider the grad students moving with their points. Well, the grad student who started here has moved out, but a little back calculation lets you calculate that some other system must have moved in, because this is a continuous path through phase space. Now, therefore, it looks, this is the wrong counting argument, that the contribution of this volume to phase space and that volume to the phase space average and so on will be the same at the start and at the finish. Yes? Unfortunately, the following is in principle possible, but you can prove it doesn't happen. As time goes on, the graduate students notice where there's the best party, and they spiral in towards the center. And therefore, as time goes on, more and more phase space points, which is what the grad students tell them to do, are piling up at one location in space, and therefore the importance of that location in space goes up and up and up. How could we imagine this happen physically? Well, suppose we had a system with friction in it. Yes? Of course, we do not have friction in Hamiltonian mechanics. Energy is conserved. It can hide someplace else, but there's no friction. But if there was friction, as time went on, all of the systems would lose energy, and therefore their statistical weights would increase, and also they would be spiraling in towards the origin, the point where all momenta are 0, and they would be packing up in a central location. Okay? Mm-hmm. Yes? Well, how do we prove this doesn't happen? Fortunately, Gibbs actually did it for us. And the answer is section 23.2, which I am not going to crank through. But the important issue in section 23.2 is if you do this very compressed 4-page calculation, which Gibbs does in about 12 lines, and you can eventually follow Gibbs if you are very patient and think very hard, but I've spread it out a bit like to 4 pages. And Gibbs shows by calculating the Jacobian. What is the Jacobian? It's the measure of how many phase space points there are in a region of space. And what Gibbs shows is that the Jacobian is independent of time, And therefore, if we start with a phase space volume here, and we allow time to evolve, the phase space volume may change shape. In fact, in general, it sort of spreads out like an amoeba being run over by a truck. But the volume does not change. And therefore, as time goes on, the graduate students do their duty as opposed to heading off to the hypothetical party. Yes? So far, so good? Mm-hmm. Okay, so Gibbs shows this. And then he shows several other things. Oh, the proof continues through pages 309 and finally runs out of steam at 311. Having done that, Gibbs then does several other things. And one of the things he shows is that the entropy is a constant of the motion. So suppose I take a group of points in phase space and calculate their contribution to the total entropy of the system. And that uses something we derived way back at the start of the previous term. And now we calculate the evolution of the entropy, the Gibbs entropy, not the Boltzmann entropy as time goes on. The entropy is a constant, because the entropy is basically some mechanical variable, log of a mechanical variable. It's W log W, where W is the statistical weight, summed over the volume. Yes? Okay, so the entropy is a constant of motion. Well, that's very important because there are all these thermodynamic tables out there. And if we had an equilibrium system and the entropy was not a constant of the motion, we had a set of steam tables, you'd have to print a separate set of steam tables for each day and time because the entropy of this steam was changing. Well, it doesn't change. It's a constant of the motion. Yes? However, there's a little problem here. Suppose, and now this proof of Gibbs, I skipped one point, assumes that the Hamiltonian is time independent. The Hamiltonian does not change as time goes on. If you have a Hamiltonian that is time dependent, the proof is not applicable. Okay, now let's consider an experiment. We have here a big container. It's got a membrane in the middle, and all of the gas is confined to this side. Yes? Now I pop the membrane, and the gas is free to expand without resistance at any time. Gee, that's an irreversible expansion if you've suffered through thermodynamics. And if you do an irreversible expansion, the entropy is supposed to increase, isn't it? Mm-hmm. But according to Gibbs, it doesn't. Entropy is a constant of the motion. So the question is, what is going on here? Well, there are a bunch of things going on that you have to be a little careful to think about. The first point is the statement the Hamiltonian is independent of time really isn't true. Before I popped the membrane, the probability of finding a gas atom on the empty side of the system was 0, which e to the minus beta u says the potential energy for an atom over here was plus infinity. When I pop the membrane, the Hamiltonian changes, and now the entropy is 0. The energy is 0, and gee, if we change the Hamiltonian, things happen. The second answer is the system expands, and the phase space volume changes shape, and it becomes more and more thread-like. Yes? However, it does not fill all of phase space. It fills the same volume of phase space it did before. It's just filled with very fine threads. And if we look at the threads through a low-resolution microscope, eventually we can't see them anymore. And the solution seems to have turned gray. And there are this is called coarse graining and is a way of treating changes in the entropy. You can also say, yes, but eventually the particles out here interact with the wall, which is independent, and when they interact with the wall, you lose reversibility because the wall does different things at different times and in different parts, and it's not in the ensemble. The last thing you can say, of course, is, well, in order to have the gas atoms in half of the volume, you had to start with the full gas volume, full volume filled with gas, and you have to wait for a concentration fluctuation that takes all of the atoms into half of the volume. You will probably have to wait a very long time compared with, I don't know, the lifetime of the universe, the proton decay time, maybe even the duration of the average PhD thesis. You have to wait a very long time. However, eventually, if you wait, it will happen. And then you discover that all of these expansions and contractions come in matched pairs. And therefore, the whole contribution of the contraction and the expansion to the entropy was zero, because you have to have two very low likelihood events happening, the first being getting the gas into the configuration you wanted it. So there are these interesting issues with reversibility. I do put in a footnote that is actually significant, and the footnote that is actually significant is that I used to encounter large numbers of students who had learned Fermi's Gambler's 3 laws of thermodynamics. You can't win, you can't break even, you must play. And all I can say is that any student who has learned that version finds it almost impossible to understand how thermodynamics works, because the impressions left with this bizarre... Have either of you ever heard that one? Mm-mm. Good. If anyone tells it to you, they're wrong. Ignore them. Because once you get those ideas into your head, it's very hard to understand what thermo actually is doing. Okay, and that takes us to page 315. Okay? And at page 315, we are going to introduce time correlation functions. Okay, what is the notion in time correlation functions? You remember our graduate students who loyally marched along watching their single system as its phase space coordinates changed. And what I had them to do was compute a function at one time, and then compute a function at the other time, and then we just took an average over each time separately. But if the grad students have a couple of pieces of paper, they could write down the value of the function as they marched in time. Or they could write down the values of two functions as they marched in time. And having done that, they could sit down and calculate equation 23.25, page 316. And 2325 takes one variable at the time t, and a second variable at the time t plus tau. Now, having said we will compute the second variable at the time t plus tau, there's something very important in there. You are doing it on the same system, not at the same location in phase space. If you did it in the same location in phase space, you calculate A at time t and B at time t plus tau, but if you're staying at a fixed location in phase space, B is a constant, and 23.25 would be independent from tau. That's the extremely dull answer. The smart thing is that you march along and track your phase space point, and you calculate A at one time and B at time tau earlier or later. And now you take the product of the two quantities. Yes? Now it turns out this is actually can be done as a single time ensemble average, because if I know the value where all of the particles are at time t, I can compute where they all are at time t plus tau, and therefore the value of b at t plus tau can be written as the value of some unpleasantly complicated function at the original time t. So I can do, this is actually is an ensemble average once you know what it means. Okay? If we are in an equilibrium system, the time separation tau matters. The absolute time of t does not matter. This is the property of stationarity. The system is stationary. If we look at all of the phase space points as time goes on, they're switching positions, but there's no change in the overall appearance of the ensemble. It's just systems are switching positions. That's stationarity. It's a very important property. The other thing you want to note and be very careful on is that there are two steps in the calculation, and you have to do them in the right order. The right order is first you calculate the product A of t, B of t plus tau for a single phase space point where you did A. Now you do an average over the ensemble, but you do the average over the ensemble after you have computed the product. If you do things in the reverse order, you get average value of A, average value of B, which is a constant independent of time, and you've sort of lost track of what is going on. There is one interesting question. If you watch carefully, I've said there are two ways to do the measurement. And one is to do an ensemble average, and the other is to have one grad student wait a really long time and march along with her point, and after she has marched with her point for a really long time, she can do a time average. And the question is, are the time average and the ensemble average the same? Well, we said this implicitly when we do, say, for example, calorimetry. You have a sample and you measure the change in temperature when you supply it with energy. Yes, you put energy in, you measure the change of temperature. And now you have the core issue. You can do a time average, you can repeat the measurement many times on the same sample, but is that the same as the ensemble average where we look at all phase space? And this is the ergodic theorem problem, and there are a bunch of statements about the ergodic theorem, some of which are more precise than others, and the more precise ones are true. There are also a few peculiar things. For example, there's something called the Boltzmann H Theorem. The Boltzmann H Theorem claims to prove that entropy always increases as time goes along, which is a very funny statement for equilibrium systems because it's not true. And the Boltzmann H Theorem has several assumptions which simply do not accord with experiment and aren't wrong. Boltzmann went off in this direction. Gibbs, incidentally, does talk about entropy increasing in irreversible processes. Gibbs viewed an irreversible process as one that linked two equilibrium ensembles that were not the same as each other. And that's where he thought irreversibility came from, when he coupled different ensembles together. Okay. So let's see. Can we do a problem here? Why don't you try problems 4 and 7? Okay. And to do 4, you're going to have to look way back to where we discussed the Gibbs entropy. because you're going to have to evaluate something, and to evaluate it, you're going to have to know what you're evaluating. And if you can't pull 4 off, don't worry about it. Then take a look at 7 and see what you can do with it.
When would you like these by? Next
Oh,
week or Friday?
sometime. Friday is okay. We have now reached the central limit theorem. Okay. It is a somewhat long proof. Many of sources that you will encounter have the unfortunate feature they use a proof of the central limit theorem that is totally wrong. I give you a correct proof of the central limit theorem, and I think we will discuss it so you know what it actually says, because the central limit theorem is often misinvoked. And next time we will do aside F, maybe somewhat quickly, and we will then do the Langevin equation, which discusses diffusion. Okay? We are done.